Off we go. All right, today's fun. Or at least I think it's fun to do graph algorithms and graph lectures. So today's kind of our first lecture. I think it's exclusively about graphs. So what are some of the topics? We'll talk about directed graphs. We'll talk about cycles, something called topological sorting, reachability, strongly connected components, and stuff like that. And what's kind of cool is that our discussion will start with just directed graphs. It's a pretty generic structure. It models a lot of things. And then at least for sake of reachability, we're going to find quite a lot of structure by the end of the lecture today. So I think it's very interesting. All right, so just in case you hadn't seen graphs before, I guess most of you have, we even have in this class. But again, we have vertices, those are those dots, and we have edges, those are lines between the dots. I always use n to denote the number of vertices, m to denote the number of edges. We can have undirected edges, which is sort of like kind of symmetric, as if you can go in either direction, or you can have a directed edge where you really can go from point A to point B and not in the opposite direction. Today's lecture will be entirely about directed graphs. Of course, you could have A to B and B to A. That's totally allowed. All right. Very quick thing, how do you represent graphs in a computer? Here are maybe the two most common ways. One is called adjacency list. I think today everything will implicitly be working with adjacency lists. But that means for each vertex V, I'll just make a list of all the edges that leave it. Okay, so that if I want to see who's leaving, I just kind of loop through this list. You could also have the reverse, where you could maybe list all the edges coming into a vertex. That's pretty simple. An alternative approach is called an adjacency matrix. This is just where I set up like a n by n table, number of rows and number of columns, both equal to the number of vertices. And if there is an edge from A to B, I'll put a 1 in row A, column B to represent maybe an edge of weight 1. If you have different edge weights, then you can do something other than 1. And if there is no edge there, we usually put a 0. Okay. I think almost all the time we'll just be doing adjacency list type of stuff. All right. So much for that. Okay, let's do some fun stuff. All right, so the first part is going to be about something called DAGs and topological orderings. All right, so what does DAG stand for? All right, DAG stands for directed acyclic graphs. Acyclic means no cycles. A cycle is, something where you could start and end in the same place. Okay, so for the first part of our discussion, we're going to look at the simpler class of graphs where there's no cycles in the graph. Okay, so if you look in this picture, all the edges are flowing from your left to your right, I think. So you can't really go backwards. A vertex that has no incoming edges, only outgoing edges, is sometimes called a source. A vertex that only has incoming edges and no outgoing edges is called a sink. Okay, so there's a source and sink labeled in that graph. All right, so these might seem like very nice graphs, but they do arise naturally. So a natural setting for directed acyclic graphs is with circuits. Okay, so I'm guessing that you guys have seen logical circuits to some extent before. Maybe here's a better diagram, right? So, okay, it's logical circuits. It's just kind of doing some Boolean algebra, but it's sort of described graphically. Okay, so sort of each vertex corresponds to some kind of logical gate. Okay, some basic kinds include input gates, kind of representing the input bits, x1, x2, x3. And then the other gates are usually taking as input 1 or 2 bits and outputting 1 more bit, right? I'm guessing many of you have seen this before, but in yellow, I've circled an OR gate. So if it's 1 or 0, it'll output 1. If it's 0 and 0, it'll output 0. You can have an AND gate. So if it's 1 and 1 coming in, then out goes 1. If it's 0 and 1, out goes 0. Okay? Or you can have a NOT gate, which just flips the bit. 0 comes in, 1 goes out, or 1 goes in, 0 goes out. Okay, so, right, so, circuits are often modeled as directed acyclic graphs. Okay, starting from the input and kind of working its way up, at least as drawn, to the output. Okay, so how would you evaluate a circuit? Maybe just speaking at a high level, right? So I give you kind of a directed graph describing a circuit. So there's nodes and edges, and maybe the nodes are annotated by what it is. Maybe it's an AND gate, it's an OR gate. Okay, and you have, I guess, 4 input bits. Right, so I want to write an algorithm to evaluate a circuit. I mean, it doesn't seem too hard. We can do it by eye in this example, right? So maybe we can walk through that, right? So let's say that you have, okay, so presumably these are all filled out with some various values, right? 1, 0, 1, 0 or something. So now which gates would I start to evaluate? Just shout out. So x1, x2, x3, x4 is filled in. What would you evaluate next? The OR gate. Okay, so we would do this one first. Okay, so we do this OR gate, and then okay, AND gate. I'm going to force you guys to say this out loud. Okay, that's a natural second choice, right? Okay, what's going on? So for the OR gate first, we have x1 and x2, so it's ready to evaluate that OR gate. For a second AND gate, we already have, I guess again, x1 and x2. We can evaluate that. All right, what might come third? Okay, maybe this one is what you guys had in mind. Okay, NOT gate, all right, because x4 is all ready. All right, now here's it gets a little bit more interesting. What might we evaluate next? AND gate, maybe this one? Okay, this is okay. And the point is that we already have evaluated this, and we've already evaluated this. Now we can evaluate the next one. Okay. All right. What after that? Do another AND gate. Fine, same idea. Just go faster now. Maybe a NOT gate here, right? We're gradually just working from bottom up, and I'm only looking at a node after all of the kind of children nodes have been evaluated. So 7th might be this AND gate, 8, 9, 10, 11. Okay, so I've drawn all the edges that are pointed up, so that means that we probably want to process from bottom up. Okay, all right, so, okay, fine. Now, that brings us to the definition of a topological order. Okay, so think of the arcs as saying like less than equal, right? In the case of evaluating logical circuits, when I'm looking at like this arc, from the AND to the OR, right? It kind of also is telling me that I need to evaluate the AND before I can evaluate that OR that's labeled 13, right? So we could think of these arcs as sort of being like a less than equal sign, right? And then that'll define some kind of partial ordering, right? Because it's sort of transitive, right? If I, look at these two edges, right? I also know that 9 has to be evaluated before 14, because 9 has to come before 13, and 13 has to come before 14, so it's transitive. Sorry? Oh, that's true. I could have just wrote less than. That's completely fine. Yeah. Yeah. Okay, so the definition of a topological ordering of V is any listing of the nodes that's consistent with, interpreting these edges as less than signs. Okay, so on the bottom, there's a topological listing of all these nodes of the circuit. And since I've hopefully done it correctly, all the edges are going from left to right. right? So I'm listing the nodes in some order that's consistent with all of the edges. Sorry. Okay. Okay, hope that's better. Okay, so you can list the vertices so it's consistent with all of the edges. All right. Now, if you had a topological ordering of a circuit, how might you now write a very simple algorithm to evaluate a circuit? Imagine I give you that topological ordering. Yeah.
Left to right.
Left to right. Okay, so once you have the topological ordering, you can just process the gates from left to right. If I'm like halfway through, I know that everything to the left has already been evaluated. I know everything I need will be on the left. Okay, so, all right, so we're kind of, but it's very intuitive, right? It's just taking that bottom-up ordering and listing it from left to right. Okay, so at some level, then the question becomes how to compute a topological ordering, how to topologically sort a graph with no cycles. All right, any ideas from first principles? Yeah. Yeah, we'll get to that, but you can do something even simpler. It is true that we'll eventually do some depth first search. Yeah.
Remove the sources and put them to the left.
Yeah, so, all right, so this can go first because it's a source, right? And this can go second, so it's also a source. Those are clearly fine at the beginning, right? And now I can imagine like erasing these. Maybe I'll just erase the edges, right? I remove them from the graph, okay? And that generates new sources, right? So I could pick this as a source, erase those edges. That's a source, I erase edges. That's a source, I erase these edges, right? And I'm just going through, and each time I'm able to find another source, I remove it from the graph, and voila. Very simple. Okay, and now I've sorted the whole graph by repeatedly just removing a source. Okay, so you do that, you'll get something, I guess, like this. This is supposed to be accurate. All right, simple. All right, so that's a simple algorithm, right? I just think of it as like a peeling algorithm, just peeling sources from the graph. While there's a source, I remove it, and I look for the next source. Okay? Not very hard to find a source, right? I just need to find a vertex without degree 0. Okay? And that's also easy to keep track of to make it fast. You know, maybe at the beginning of the algorithm, I just go through and I count up the edges and I figure out everyone's in degree to start. Right? That takes linear time. Now, as I remove vertices from the graph and I remove edges, I update those degree counts to find the new zeros. Okay? So, all right, that takes linear time and it's conceptually pretty simple. Okay, any questions? Sorry? Sorry, the algorithm is? Oh, the output is a list of vertices that are in order. Yeah, so yeah, append V to the output list is where we're gradually building out that list. Yeah. Okay, other questions? All right, now it's part 1. Part 2. All right, searching graphs. Okay, so here's I guess I thought it would be helpful to think of some real life examples of graphs. Okay, so here's a problem I face every Monday and Wednesday. my office is here, and we are, where are we? Are we here? Okay. So then I look at the map and I figure out, I want to know if I can get there or not. So I usually go out this door, and then I cross this street, and I go over here. And then here I do some bizarre diagonalish thing. I usually go here. And then today I was late, so I was actually running. And then I usually come through that door. Okay. But you look at a map and you want to know if you can get from point A to point B. That's a basic kind of problem that we'll look at today. Here's maybe a more fun example that I saw on the internet one day. So here's the puzzle. You have a bunch of cats. Okay. One is labeled a start cat. Another is labeled the goal cat. You want to get from start to goal. Okay. And the rules are, you see that some of the cats are facing forward because they have eyes, and some aren't because they don't have eyes. So you can go from forward to back to forward to back to forward to back, and you want to, I guess, hop on these cats from start to finish. Right? So at the beginning, you can go like this and like that. That seems to be your only choice. Okay. Give you guys like a little bit of time to stare at it, see if you can solve it. We're still working on it. All right. Anyone solve it or decide that it's impossible? Anyone thinks it's impossible? Okay, that's like 70. Whoa. 70% no. And who thinks it's possible? Okay. 4 yes. Who didn't even try? Okay. All right. So let's try to do it together. All right. So from here, I guess you would have to go here. So anyone who was able to, or anyone who didn't solve it, right? Whatever. Should I go right or down? Right or down? Someone say. We'll go right. Okay, go this way. Should I go right or down right? Right. Okay. And then I guess I have to go down. And then I guess down. That's what you guys have in mind. Okay, down. Right, down, or left? Right, down. Just pick one. It doesn't matter. I'm at a dead end? Well, no. I mean, there's three eyeball cats right next to me. Left? Okay, we'll go left. Okay. Uh, Down or down left? Down. Okay, and I guess down again is okay. And then maybe should I go down? Okay. All right. And then down. Okay. Right or down right? Down right? Down right? Okay. Right, I guess, is the only choice. Now we're at a dead end. Okay. Uh, what if I went right? Okay. Then you go right. Now what? Okay. Doesn't matter what color or size they are. We can go up to the secret cat. There's a cat in the middle of the cats. That this the blue in the middle is a cat. It's a blue cat. It is the shape of a cat. Okay. Uh, and from here you can go to the right, down, down, right. Okay, good. We solved the cat puzzle. All right. Okay. All right. So we're going to roughly be working on this problem, but with like less optical illusions. Okay. So here's a simple directed graph. So A can reach B if I can follow edges to get from A to B. So take this simple graph. Can S reach all of the vertices? Give you guys a chance to stare at it. Okay, who's not going to vote? Okay, you're all on the hook. Who says yes? Okay, 3.5. Who says no? Probably like 5. Okay. All right. So for no, why did you say no? The right answer is no. Yes, I'm not sure this is what you had in mind, but I planted like a triangle in the middle, and there's no edges going into that triangle. So you can't get into the middle triangle. Okay, but hopefully, I mean, this is a pretty small example, right? There's like, I don't know, 12 nodes or something, and you should have had to stare at it for like a little while. So it's not like these problems are that easy, even for n equals 12. And then our goal now is to make an algorithm to figure this out automatically. Okay, so one thing I want to point out, if we're just like looking at a map here, it's pretty easy if you can reach from point A to point B or not. But this is partly deceptive because you kind of have a bird's eye view of the whole thing. And the perspective of the algorithm is maybe a little bit more like using Google Street View, right? Where you're just kind of looking at one node and its edges at a time and then gradually maybe building up some information. But, just to keep in mind that you are kind of searching through a graph. The other analogy, again, a maze, not that this is easy, but it's much easier to do a maze when you're staring at it from up above and it's like on your placemat at TGI Fridays or something, as opposed to actually being in the maze, in which case, like, good luck, right? Okay. But in the maze is a little bit more like the perspective being taken by an algorithm, at least in my opinion. Okay. So let's just try to go about this problem from first principles. I know many people have seen some of this stuff before. But imagine we kind of did the kind of thing that we've been doing for the first couple of weeks, right? Okay, so I'm going to look at a slightly more restricted problem where I have S and T in the input, and I just want to know if S can reach T. Okay. And I might try to write a recursive algorithm for this because that's what we always do. So here's a reasonable sentence. I wrote recursive search ST. It'll be true if S can reach T and false if not. Okay, it seems sensible. Okay. And in implement, again, I think there's nothing special going on here. Okay. Recursive search ST, if S is equal to T, okay, I've reached my destination. I just return true. Okay. Otherwise, I know that if S could somehow get to T, right? There must be some first edge, right? There must be some neighbor V. That V can reach T. Okay, so I'll just try all the edges SV, so all the edges leaving S, and I'll recursively call recursive search VT to see if V can reach T. If any of those return true, then great, I'll return true overall, right? Otherwise, I'll return false. It seems reasonable. Okay, so that's the simple idea, right? Okay, if S can reach T, then there's some intermediate vertex that I'll try out. Okay, and recursively, that recursive search VT will return true. Sounds okay, right? All right, any issues with this? Yeah. Okay, so what happens on something like this? Right. So if you take this simple example, if S is like in this triangle, then we'll just keep recursively going around and around and around that triangle, and actually the algorithm will never terminate. Okay, but it's a bit odd because it looks like everything we've been doing for the past couple weeks. So, what was wrong in the argument? The argument looks reasonable. Somewhere there's a lie. What's wrong with the argument? Yeah. Yeah, so for recursion to work, you actually need some induction to be correct. So the inductive hypothesis is that there's something smaller that works. But here nothing is really getting smaller. The change state hasn't changed. Okay, so you can't just always call recursion, right? If you're not actually nibbling away at the problem in some constructive way. All right, so our next question then is, how do we fix this? So maybe as a thing, if you're literally doing a maze on a piece of paper, what do you do, like physically? Yeah, you would get out a pen, right? Or pencil probably, and you would just start writing stuff, right? You got stuck, but you kind of know where you came from. You can backtrack, keep going forward, right? So it's like a Hansel and Gretel kind of thing. You can leave breadcrumbs to everywhere you've already gone, so that you don't revisit the same place twice, which you already knew because you've done these all through your childhood. Okay, so that's basically the only idea we're going to introduce to the recursive algorithm. That's going to calm all our problems. Okay, so then here is depth first search, as was mentioned earlier. So depth first search, DFS, is an acronym for depth first search. Okay, it's depth first because we're going to kind of search a vertex and then keep searching right away. Probe deeply. Okay, so all I've really done is add this marking. The only difference from our first naive algorithm is we've added this marking stage. When I visit a vertex, I see if it's marked. Initially, they're all unmarked. If it's not marked, then I mark it right away, and then I do the search. If it is marked, I've already been here before, I'm not going to look at it again. It's not so different from the principles behind dynamic programming. I've already looked here, I won't look again. Okay. So, just to make sure we're on the same page, I thought we'd simulate this algorithm. If I call depth first search S, and you guys just tell me at some level what's the next vertex we go to. right? So I guess I can go left or right or just pick one. Okay. All right, so you go here, right? This is unmarked. So we mark it, and then we keep searching. Where would I go next? Left or, okay, left. Okay, I mark it. Okay, and now there's actually no outgoing edges left. So this would just return. Okay, and now where do I go? Down, okay. I go here, I mark it, and then down-ish. Here, I mark it, and then return, I return, I return. Okay, now where? Oh, it's not so easy. Okay, I don't return. Okay, now I go. Okay, so I don't see why we need AI when I can't do these basic things. All right, I check it, I mark it, and then down to the right, I mark it, and then, okay, I mark it, and then, okay, and then, okay, I'm just trusting you guys on this now, and then, okay, and then, okay, and then, okay, and then, okay, we are here right now. So what do I do from here? Okay, we still return. All right, now what? Go right? Okay, let's go right. Okay, check that off now. Yeah, we'll go down right, and now we've actually run into a vertex we visited before. So we just return. Okay. And now, gotcha. All right, we mark this off, and then, yeah, so it'll try this edge, find that it's marked, and then it'll return. Okay. Oh, return again, and then, okay, and then, actually, it won't return yet. Yeah, there's one edge we hadn't tried. This was already marked. Then it'll go back. And now we've explored all the edges that leave S, and finally it'll return. So we end up traversing all the edges except those leaving vertices from that hidden triangle in the middle. We never visit that triangle in the middle like you ought to have expected. Okay? Simple enough. All right. Okay. Let's make two simple claims. Claim one is that it's fast. It'll run in linear time. Claim two is that it'll visit all the vertices reachable from V. That's the more interesting thing. Okay. Who wants to explain why it runs in linear time? Yeah. Yeah, okay, so yeah, let me just sharpen that a little bit. Okay, so I'm only going to go on an edge from U to V right after I mark U or visit U for the first time. And I only mark each vertex once. So I only traverse each edge once. Okay, nothing more than that. Okay, here then is the more interesting claim. Okay, the claim is that if I run depth first search from V, or I guess S previously, I will visit all the vertices reachable from V. I won't like leave some out. Okay. And here we'll do a slightly different proof style than I think we've ever done to this point. I'm going to do a proof by contradiction. Okay. So I'm going to say, suppose there is some vertex W that's reachable from V, but wasn't visited. particular, it wasn't marked. And I'll show, okay, there's something wrong. There's some contradiction. Okay? Which means the premise was impossible, so W must have been visited. And here's how we'll set it up. I'm letting A denote the set of all the vertices that are marked. Okay? And I'm letting B denote all the vertices that are unmarked. The same as vertices that are visited and not visited. And then W is some vertex reachable from V that by contradiction is not visited, so it's in the set B. Okay. Now, all I know about W is that it's reachable from V, right? So there's some crazy walk in the graph. There's some way to get from V to W, right? And all I really know about this walk is that it starts in red and it ends in blue. That guarantees that there's at least one edge that starts in red and ends in blue. Here's that edge. It could be that edge from A to B labeled in that picture. So A was marked, but if A gets marked, A is going to visit all the vertices leaving A. So B would have to get marked, except supposedly B wasn't marked. That's our contradiction. Okay, so there must be some edge going from red to blue, but then that's impossible. As soon as I mark a vertex, all of its outgoing neighbors will then get marked. Okay. All right. There's other ways to prove this too, but that's just one. Okay. Good. So those are just some basic facts. Yeah, in fact, we could have refined that argument a little bit more, where you can just trace the path and see that DFSV also only returns after all the vertices reachable from V have been marked. All right. Fine. That's in the part 2. All right. Our last part is going to be about sorting graphs in general. At some level, we're going to try to take some of our discussion from DAGs, which had no cycles, and generalize it to graphs with cycles. Okay. Any questions about DFS though? All right. Okay, so remember at the beginning we talked a little bit about how to topologically sort a graph. Maybe the conceptually simplest way is to repeatedly remove sources. Okay, and that can be made fast. It's not a complicated algorithm. Now, but someone else suggested DFS, so let's probe that idea. So, if we look at what DFS does, right, and I call it DFS of V. Between the time that V is marked and DFS of V exits, okay, DFS will only search vertices that are reachable from V. Okay, that we've sort of established. And actually, it's only going to return once all the vertices reachable from V have been marked. All right, so let's look at this lemma. Okay, so suppose I have a situation like in that picture. So I have two vertices V and W, where V can go to W, but W cannot go to V. A little asymmetry. Okay. The claim is that if I run DFS and I end up visiting both V and W, okay, that DFS must finish searching W before it finishes searching V. So if V can reach W, that means that whatever depth first search is doing, even if I call depth first search on some other vertex, so it's doing other funny things, it'll have to finish its call to DFS W, like when you mark it and exit, before you finish marking an exit at V. Okay. All right, so I think this probably is not too surprising a claim. It should agree with your intuition. But let's prove it and go through two cases. Okay. All right. In case 1, DFS maybe marks V first. right? So it visits and marks V. Okay, but now it starts searching its neighbors and stuff like that. So we want to claim that in this case, we will search, mark, and finish searching W before we exit from that call to DFSV. Okay, and why is that? Yeah. Oh, okay. So the suggestion was if you finish searching V before searching W, that's the contradiction, then there must be a path from W to V, which we said there isn't. But I feel like there's a gap there. Like, I'm not sure why finishing W implies a path from W to V. Well, okay, so one thing is we can recycle one of these observations from up above, which is that DFSV will visit all the vertices reachable from V and only return after all the vertices reachable from V are marked. So we can just kind of drop in this statement, which in it has an argument not dissimilar to what you suggested. So this is case 2. Wait, sorry. Uh, it's a bit of an odd statement because maybe this is so obvious to so many people. The claim is that if I call suppose you're running some depth first search, you started from some other S, right? And suppose it eventually marks V and W in some order, W searches and suppose it marks V first. So first it visits V. And the claim is that it will visit and it will visit and exit DFS, exit W before it ends up exiting V. Yeah, right. Okay, I think we're probably on the same page on two sides of the same coin. Okay, good. All right, so, okay, fine. But this is just, anyway, the point is that that previous lemma is roughly what we're looking for. And then something similar, okay, suppose depth first search marks W first, right? And now I'm worried about, I want to say what wouldn't happen is it goes off and searches V before it finishes W. But this wouldn't happen because? So if you call DFSW, you only search the vertices that are reachable from W. That's what we've established. And so particularly that excludes V. Okay, good. Because there's no path from W to V. Okay, awkward enough, but hopefully we're okay with the statement. And yeah. All right, so, okay, so that's just the point. The point is that if V can reach W, but W cannot reach V, DFS will always finish W before V. Okay. Now imagine I took the depth first search code and I appended one line where I just print out the vertex as I'm exiting the thing. And I just want to say, oh, what does this list of vertices look like? Right? So, that's going to print out some set of vertices in some order, right? This will be the first vertex that depth first search finished on, second vertex, third vertex. It'll print out some vertices in some kind of order. Okay. Now, what do the edges, like if I transpose the edges onto this ordering, what would it look like? I guess my question is, can it look like this? Can it look like that? Can I get edges in all directions? Or is there some structure? One way. Someone said one way. So which way will the edges point? Okay, I heard left to right. Okay, I also heard right to, okay, we'll have a vote. Okay. Who thinks, okay, who's not voting? Excellent, one. Okay, who thinks it's going to go from left to right? Okay, one, brave soul. Who thinks it's going to go from right to left? Okay. All right. So it's going to go right to left. So, because if V, okay. So if you have an edge from A to B, then B has to get printed before A. That's what the previous established. So it's some opposite of the lemma, the contrapositive. Okay, so if you run, right. Oh, okay, I cheated a little bit. Okay. Okay, that's the question was meant specifically for DAGs. Okay, because that's where our lemma applied. So in a DAG, if A can reach B, then B cannot reach A because there's no cycles. Okay, so that's the setting in which our lemma always applies. So I forgot to mention that. Okay, but okay, so as you guys have already mentioned that if you can reach V, then depth first search will always print V before U, and consequently, like you guys said, you will get all our edges corrected from right to left. Okay, so if I use depth first search to print out all the vertices, okay, then what does the ordering of the vertices look like? Or what is this? Yeah, perfect. The topological order actually went the other direction, so it's in reverse. Okay, so it's actually printing out all the vertices in reverse topological order. And so that gives you a second algorithm for computing a topological order. Okay. The only thing I'll point out is that if you call depth first search from one vertex, you might not visit everyone and print everyone out, right? So what you would do is you just add like a loop around it. Maybe I'll call it like a driver, okay? And just say, oh, while there's some unmarked V, so you just loop through all the vertices, check to see if they're marked. While there's an unmarked vertex V, I would call depth first search at V, and that makes sure everything gets marked. And that can just append all the orderings, and that's fine. Okay. All right. Okay, so that gives us two algorithms for topological sort, and now here's where things get, I think, more interesting. Okay, because here's now we're going to, yeah. It could be a what? Oh, no, we're saying it does. So if we're looking at a DAG, so the graph has no cycles, okay? Then from looking a little bit carefully to what DFS does, if I can go from point A to point B, but not vice versa, which is always the case in a DAG. So if I can go from point A to point B, then depth first search will always finish B before it finishes A. So if I'm printing out the names of these vertices as I finish, B will always get printed before A. It'll print 2. Yes. That's fine. So 2, yeah, okay, so let's go through your example. So you said, okay, let's say I have vertex 1, vertex 2, vertex 3. Okay. And the first thing I'll do is I'll go to 2. I'm starting at 1. I'll go to 2 and I'll print out 2, right? And we'll go back. I'll print out 3. I'll go back and then I'll print out 1. Okay. And if I look at what the edges look like in this graph, if I kind of draw it on this ordering, I have an edge from 1 to 3, and I have an edge from 1 to 2. So all the edges are going, in fact, from right to left. Now, for what it's worth, the topological ordering is not unique. I can interchange 2 and 3 here, but yes, there may be more than one topological ordering. All right. Okay, so the next part is going to somehow be trying to, somehow things are simpler in DAGs because there's no cycles, right? And you get these topological orderings and stuff like that. You don't have that in a general graph, but we're going to see how much of this can in fact carry over. Okay, so here we have to introduce the notion of strong connectivity. So strongly connected just means you can go from A to B and from B to A. They're mutually reachable. Okay, that can happen in a general graph. It can't happen in a DAG because that would imply a cycle, but it can happen in a general graph. We say a graph is strongly connected if every pair is strongly connected. So I can go from any point A to any point B and vice versa. Okay, fine, simple enough. Okay. Sort of a technical claim and probably not a surprising one. So strong connectivity defines an equivalence class, but which I mean in particular, if A and B are strongly connected and B and C are strongly connected, then A and C are strongly connected. All right, so I think equivalence class is sort of an over-the-top word for it. It's not so hard to see. So here's 3 vertices. U and V are strongly connected. There's some walks connecting them. And V and W are strongly connected. There's some walks connecting them. I want to argue that the outer vertices, U and W, are strongly connected. But this is quite clear from the picture, right? I can concatenate the walk from U to V to U to V to W, and now I'm able to get from U to W. And of course, in the opposite direction, if I wanted to go from W to U, then I know that I'm able to get from W to V, and I'm able to get from V to U. That gives me a way to get from, interesting. That gives me a way to get from W to U. Okay. All right, so no big deal. Okay, great. So each of these quote unquote equivalence classes is called a strongly connected component. Okay, so it's a set of vertices, it's maximal, and it's strongly connected. Every pair of vertices within, okay, so here I've taken that graph we've been working with, and I've colored them according to the strongly connected vertices. Okay, so like that green triangle in the middle, all 3 vertices can reach each other by just going around that triangle, right? Same with yellow, which actually breaks down into like 2 cycles, it looks like, but they can all reach each other. Okay. The purple on your left is another strongly connected cycle. We have 2 vertices down at the bottom that can't go anywhere. So those are their own strongly connected component. Okay, so one of our goals is to sort of identify all of the strongly connected components algorithmically. Okay. All right. So let's start small, not worry about getting all the strongly connected components. Let's just fix a vertex V and try to find out the strongly connected component of V. All right, any ideas? Sorry? Okay, so I can call DFSV, right, like what we just did, and find all the vertices reachable from V. Okay, so this will get like half of it, so to speak. Okay. Fine, but that's not all, right? Because yeah. V is reachable from what? Okay. So technically every vertex can reach itself because you don't have to take any edges. Yeah.
I think if you can reach V from V, every all the vertices along the path corresponding
If you can reach,
V from V.
you mean like if there's a cycle? Ah, okay. So if there's a cycle, yes, everything is okay. But finding a cycle is also another challenge. Sorry?
You can have DFS for all these vertices and see if V lies in those cells.
Okay. So then, okay, so the first call DFSV finds all the vertices V can reach. So the natural idea is to loop over all the vertices besides V and call DFSW. Okay, and if V is marked, uh, then that means W can reach V, right? Okay, so in other words, I can call DFS once from V to figure out everyone V can reach, and then I can call DFS from everyone else to see who can reach V. And how long would that take? Sorry? Yeah, so I guess maybe n times n plus n, but that's roughly the same thing. Okay, because I'm calling depth first search n times. Okay, so the slow part is obviously the second step. Okay, is there a better way to figure out all the vertices that can reach V? Yeah. So at the beginning of depth first search, if the current vertex is V, return true. If the current vertex is not V, return false. So, one sec. So if I just call depth first search V, it just returns true and I'm done? Oh, except for the first one. Oh, okay. So if I, okay, so it is true that, okay, I maybe I'm doing depth first search starting at V and I visit some vertex W, okay? And if I find some back edge back to V, then yes, then W would and can, yeah, I know I can go there and back. But okay, so if at some level, then I can try to like back propagate basically this information back up. Okay. How long will that take? So, okay, so trying to do some, okay, so at the very least, I'll suggest that this is not simple, right? It's a little bit complicated. I'll suggest there's an even simpler way to go about this. I want to figure out all the vertices that can reach, yeah, okay. So this is one of the most important tricks in the in the class. Sometimes you don't change the algorithm, you change the graph, you change the input. Okay. So what happens if I took a graph like this and I reversed every single edge, right? I'm just reversing everything. Okay, so I flip all the edges. If I call depth first search from V, I get all the vertices that V can reach with the edges flipped. Those are exactly the vertices that can reach V in the original graph. Okay, so we just flip the edges. We don't have to reprove anything. Okay. All right, so simple enough, right? Instead of doing something a little more involved, and more involved things are possible. Certainly, you can reverse engineer what flipping and running DFS would look like, right? But yeah, the simplest thing is just reverse the edges, run depth first search, and you get everything that can reach V. And then you just combine the two sets of marked vertices, and that gives you the strongly connected component of V. All right, but that's an important idea. Sometimes you don't want, oftentimes you don't want to change the algorithm. You just want to change the graph, because then also everything we've learned and studied about depth first search, we get for free. I don't have to reprove, reestablish anything. I just have to reinterpret it on my input. Okay. All right, so again, how long would this take? The first depth first search would take m plus n time. The second one, again, is just a depth first search with the same number of edges. M plus n time. I combine them, that maybe takes O(n) time. And overall, it takes us m plus n time. Okay, nice and cute. All right, so, okay. So now at some level, what happens if I want to get all of the strongly connected components, right? Our goal ultimately is to get all of them, right? What's a natural idea based on what we've done? Yeah, I could run this for every vertex. Oh, that's true. So maybe when I find one strongly connected component, I can scoop it out of the graph. I thought there was something written here. Okay. Yeah, we can roughly run it from every vertex, or you can, scoop some out along the way. In the worst case, you might be running it from a lot of vertices, though. So overall, your running time would become, n times m plus n, so roughly mn time. Okay. The question is, can we do better? So right now we know how to get a single strongly connected component in linear time. I can just run that over and over again until I get all the strongly connected components. Can I do something faster than that? Okay. All right, so consider this. What I've done here is I've taken our graph of the strongly connected components kind of colored, and I've contracted each strongly connected component to a single vertex. So I've sort of taken that whole yellow continent and kind of shrunk it to a single vertex, right? Treat it as a single vertex and then retained the edges in between. So you'll see they kind of match up. There's a vertex corresponding to a green triangle in the middle, a vertex corresponding to a purple triangle on the left. Okay. So I took the strongly connected components, I contract each one to a vertex, and that gives me like a smaller auxiliary graph, where each vertex in this auxiliary graph can be interpreted as one of the components in the original graph. Okay, it looks nice, it looks pretty, but there's something conspicuous about this smaller graph. Besides the fact that it's smaller, it has a nice property. Acyclic. There's no cycles in the contracted graph, because if there was a cycle, those two would have to be combined to make a strongly connecting component. So when you kind of treat all vertices the same based on their equivalence class, then there's no cycles left, right? There's no cross things. All right, so, okay, so it's a DAG. Okay. Now consider this hypothetical. Okay. Right, so here's our current approach, right? And this, I guess, is scooping everything out. So our current approach is, as long as there's some vertices left in the graph, take some vertex, compute a strongly connected component, label each vertex, that's component 1, component 2, and remove it from the graph. And that's taking like mn time. Okay, so consider this hypothetical version of the graph algorithm, which doesn't totally make sense yet. So I'm going to call it sync first, strongly connected component. And all I'm really changing is which vertex I'm going to choose when I'm calling SCC. Okay? So suppose, let me leave this here to keep it simple. Okay. So before we're just choosing any vertex and then getting a strongly connected component. But suppose I always chose a vertex from a sync component. Okay? So that means like my first choice of vertex would be maybe that red vertex down at the bottom. The second choice of vertex might be the other sync vertex, right? So that'll be 1 and that'll be 2. And once these are, and that might be 3, right? I might do the green vertex third, because once those other two are removed, okay. And then maybe this would be fourth, and that would be fifth. Okay, but I would take a vertex out of a sync component, sync component, sync component, sync component, sync component, and call strongly connected components. Okay. Now, there's a couple things that are nice. So if I call SCC, say on this red vertex in the bottom left, right? Or if I call depth first search, right? I know that everyone I visit, I'm going to visit whoever I can visit, but I'll never leave the component because it was a sync component. So I can actually just call depth first search instead of SCC, which is even simpler because SCC had 2 depth first searches, including in the reverse graph. Okay. So one thing is that I can take this line and replace it with depth first search V, because depth first search will never leave the sync component. So now I just call depth first search everyone who visits that's in the same component. And then I'll rip that out of the graph. Okay, so the two changes, the main change is I'm always choosing a vertex from the sync component when I'm looking for a strongly connected component. And knowing that I can't, or I have a vertex in the sync component, I only have to call depth first search instead of doing this reverse thing. Okay, those are the two changes. And the only reason I'm cheating is that I don't know yet how to get a vertex from the sync component. We're going to address that afterwards. Okay. If I did it this way, and assuming I could get vertices from the sync component for free, how long would this algorithm take? So the nice thing is that I start searching at a sync component, and I never leave the sync component. I might visit like 100 vertices, but they're all in the sync component. And all the edges are within the sync component, and I rip them out of the graph. So actually, everyone that gets marked and all the edges I traverse are going to get ripped out of the graph right afterwards. So all put together, we actually only mark each vertex once, and we only traverse each edge once, because I can never leave a sync component. Okay? So as a result, when you put everything together, you actually get a linear time algorithm. So if I was able to find vertices from the sync component in the next 2 minutes, then we would get a linear time algorithm. Okay, so that's our next challenge. Okay. All right, so that's right. So if I can figure out the sync components, then I only need to run one depth first search, and it's only going to take linear time total. And the only question is, how do I find the sync component style ordering? Okay. Any ideas? Okay. Let's look at our post-order traversal again. Right? So if we actually call depth first search, right? So what do we prove? If A can reach B, but B cannot reach A, B will always get printed first. That's what we know. And that holds for any graph, not just DAGs. It has a clean interpretation in DAGs because it gives a topological order, but the lemma itself holds for all graphs. So if I run post-order DFS and I print out the vertices at the end of each DFS on our original graph, and then I list the vertices and I draw the edges, right? The edges within a color, A can reach B and B can reach A, they can go in different directions because we don't have any guarantees about what happens when A can reach B and B can reach A. But if A can reach B and B cannot reach A, so they're in different strongly connected components, B will always get printed first. So if you look, what will happen is that all the edges that go across colors, across strongly connected components, they're always going from right to left. We only have guarantees on those edges. Okay? So that's right. So all the cross component edges in blue are in the same direction. Okay, so how are we going to use this nice property? Remember, the goal is to be able to extract vertices from the sinc component very quickly. Now, from looking at this picture, it might be tempting to say that the first vertex listed is always from a sinc component. However, that's not quite true. Instead, we have the following very similar observation. So let me state a little bit more generally. Suppose V1 through Vn list of vertices, so that, like the post-DFS order, if Vi can reach Vj and Vj cannot reach Vi, then I is greater than j. Then, although I can't say anything about the first vertex, I can say something about the last vertex. I can say that the last vertex is always from a source component in the graph. And it's easy to show this by contradiction. If Vn wasn't from a source component, then Vn could reach some other vertex, call it A, and A cannot reach Vn, and A would have to be listed afterwards. Okay, so we have this lemma saying that whenever we have something satisfying this kind of nice ordering based on reachability, then the last vertex is always very well behaved. Okay, so how are we going to use this? So remember, the goal is really to figure out how to implement this step. How do I extract a vertex in a sinc component iteratively? Okay. And now we have a lemma that's saying that I know how to get vertices from source components. And I should note that you can actually iterate on the lemma. For example, if I remove the source component and then I have some remaining list V1 through Vn minus 10 or something, then again, the last vertex will be coming from a source component in the remaining graph. Okay, but yeah, to highlight what's going on, I really want to figure out how to get vertices in the sinc component, and I'm stuck trying to figure out and I only have a lemma that lets me get vertices from source components. Okay, so how do we rectify this? Okay, you just need one simple trick that we used before. So if I can only get vertices from the source component, but if I want to get vertices from sinc components, we're not going to change any algorithm. We're going to change the graph. We're going to look at the reverse graph. We'll reverse all the edges, run post DFS on that, and then the last vertex will be coming from source components in the reverse graph, and those are sinc components in the original graph. So here then is the ultimate algorithm, right? There's one final trick. In the first step, we just compute the post DFS order once in the reverse graph, G sub R, and now to keep getting vertices from the sync component, I keep getting vertices in the last remaining vertex from that post-DFS ordering we computed in step 1. Since that's from a source component in the reverse graph, that'll always be coming from a sync component in the original graph's G. The rest of the steps are the same as before. We run DFS from that vertex, get the component. We output that as one of the components, remove the component all its edges, and repeat. Okay. And that's it. And amazingly, this whole thing can be done in m plus n time, linear time. In some sense, this is pretty spectacular because we're sort of sorting the graph in some sense, decomposing the strongly connected components and even listing them in reverse topological order in time faster, and you can sort n numbers or m numbers. Okay, so it's pretty spectacular. All right, thank you very much, and next time we'll do shortest pass.